Okay, hi, I just wanted to show you some of what we do when we prep food samples for digestion. These are some raw material samples that we have. You might be able to see in there maybe about 0.25 grams typically of sample material. I think here's a chlorella tablet or a spirulina tablet perhaps. These are all recorded in the database, and then we come over here to prep them for the digestion in the hot block. And first we turn on the fan in the fume hood. This pulls air through here obviously to prevent us from being harmed by fumes from the nitric acid. And this is a 69% redistilled nitric acid formula here that turns food solids into liquids. So this is much stronger than human gastric acid. This is a very, very powerful oxidizer, and I wanted to show you the way we actually process these materials. So these right here, let's see, 893, 892. These here are actually samples for our store. These are materials that we're going to consider packaging at the Natural News store. But before we sell anything, we test it here, and it has to pass our stringent quality control standards, which are much more stringent than anybody's in the entire world. In fact, more stringent than Health Canada, more stringent than FDA, more stringent than the EU. Nobody has as stringent standards of heavy metals as we do. So what I'm doing here is actually, wait a minute, let me get this. There we go. I'm putting these in order in the digestion tray. Oh, you may wonder why am I wearing this mask. It's because sometimes when you put acid in these products, they explode. You might see some explosion marks in here actually. Well, look what it does to this label. It turns the label brown. This material here is a sulfur embedded cloth that is designed to absorb acid. This right here is what happens when you take a penny and you put nitric acid on the penny. It turns it blue and it fizzles, and it generates an excessive amount of heat, actually melted part of the bottom. I was doing a demonstration with that. So this acid here is very, very powerful, and we have to be extremely careful. I'm wearing the latex gloves. I'm wearing the lab coat to protect my arms from an acid explosion or an acid spray of some kind, and then the face shield obviously to protect my face. I have a lot of different external standards in here. All of these are toxic. This is 1,000 parts per million mercury, as the label says right there, with an exclamation mark. This is 1,000 parts per million gold that I use to stabilize the mercury in digestion solutions. Gold and mercury naturally bind to each other, which is well known in the mercury or the gold mining industry. This is a custom external standard of 100 parts per million of aluminum, arsenic, cadmium, copper, and so on. This is a custom formula we put together. Here's a radio spike that I use to test for certain types of isotopic absorption by certain food materials. In any case, what we do here is we, with the fume hood on, I take the lids off of these and I keep them in a very specific order. And one thing you'll notice is that the lid and the vial are both labeled. This is for a quality control process. So the lid here says M893, but also the vial itself says M893. That way, if the lids or the vials get mixed up, we can always reestablish what they are. Now, if these were off-the-shelf products that I were testing, I would be testing 3 different samples of each off-the-shelf product. But right now, since we're just doing an initial check of whether we're going to accept or reject a raw material, we're just doing one test right now. But after we manufacture the product, if we accept one of these materials and then we manufacture a product, we will then test that resulting lot 3 times to make sure that the results are very, very clean at the end. Also, if we get a very strange result here from some unusual contamination, for example, then we would simply retest it to get a confirming check accomplished. All right, now that we have all the lids off, we're going to dial this in to the milliliters that we want, which in this case is 10 milliliters. And this is what dispenses the nitric acid. And I'm going to put 10 milliliters of nitric acid into each one of these vials. And as I do that, sometimes materials will smoke. They'll produce a blackish, brownish type of, it looks like smoke. It's obviously not fire smoke. It's really a gas from oxidation. But I'm going to go ahead and start putting 10 mils of acid into each one of these vials. Okay, so now that I've finished the digestion, I just want to show you this up close. There's 10 mils of nitric acid in a food starting to dissolve and digest whatever food powder this happens to be. And now we have HEPA filtration running in the room to prevent dust from getting in here, but the airflow is also going up and out because of this fume hood. So the risk of contamination is very, very small. However, this is not the same as like a semiconductor clean room, where they have very, very low tolerances, parts per trillion. We're not dealing with parts per trillion. Typically, we're dealing with low parts per billion type of levels here, which is a lot easier to deal with. But this chlorella or spirulina, whatever it is already starting to digest by itself. Next, we add what are called watch glasses, because as these vials begin to digest and off gas, you can actually lose a lot of heavy metals into the air if you're not using these watch glasses, which look like this. And what they do is they allow the gas to escape the vial without sealing the vial, because sealing the vial would be a huge mistake in this context, because it would build up extensive pressure and it would cause an explosion. Now, there is a different digestion process that we use with another machine that I'm not showing on camera, because it's called a closed cell digestion system, and it's a lot more elaborate, and it's one of our secrets here of how we do that. But whereas this hot block is a more commonly known procedure. But a closed cell digestion system is great for digesting things like fish oil samples, or believe it or not, turmeric resin is highly explosive. So is fish oil. If you take marine oils, and if I were to put like a fish oil capsule in this vial and just put acid in it, it would explode all over the place. It would be quite a mess. So next I'm going to set this on a 2-hour digestion cycle here, and then we take our vials, so you can see them here. Here they are, ready to go, and we drop them into the digester, the hot block, and then we let them go for 2 hours. And as this digestion begins, again, they will start to off-gas significant quantities of like a smoke or a vapor, depending on the material. Like I said, copper produces this kind of blue smoke that I had to neutralize with baking soda. But every different food gives off a different color. And I have this set right now on an external temperature of 100 degrees Celsius, which means the internal temperature inside the vial is going to be about 90 degrees Celsius to 95 degrees Celsius. And that's a pretty good temperature for most of what we do. Now, during digestion, I close the fume hood down to protect from, or at least most of the way like this, to protect against explosions. So just in case I've miscalculated something, if there is an explosion, it will only hit the plexiglass, and it won't actually come out into the lab and come onto me or the face mask or the clothing or whatever. When you get this acid on you, it'll turn your skin yellow and it burns. It actually produces a burn. It'll burn your skin right off. And I'm not going to demonstrate that because, well, for obvious reasons. But all right, so that's how we process these samples for digestion. And I should have told you beforehand that each of these samples is very precisely weighed using a laboratory analytical balance or scale, which in our case is accurate to 4 decimal places of a gram. So it can measure 0.0001 grams with accuracy and consistently. And after we normalize these samples with a very specific volume of liquid, we can then calculate the dilution ratio, which since these vials are 50 milliliters, typical dilution ratio using a 0.25 gram sample might be 200 to 1. So whatever concentration of heavy metals are then found in these products by the mass spec machine, the ICP-MS, through the mass charge ratio analyzer / detector, you would multiply that by 200 to get the actual concentration found in the original raw material. That's important to understand because that's why you have things like this, pipettes, because you have to use precise volumetric measurements and liquid volumes in order to get accurate results at the end. So there's really a lot to this. I know that some people have thought, well, oh, this is easy. You buy a machine, you take a sample, you pop it in the machine, you hit go, and you get your answer. It's not like that at all. It's actually a very complex, multi-stage process where the operator, the chemist, let's say, needs to have a very deep understanding of volumetric measurements and how you make external standards, for example. For example, if I take 1,000 parts per million of mercury, and let's say that I want to make an external standard that is 10 parts per million mercury, how many milliliters of this would I put into a 50 milliliter vial? Well, the answer is 0.5 milliliters. So I take 0.5 milliliters of this and 49.5 milliliters of a blank solution. That would create an external standard of 10 parts per million mercury. But by the way, we would never run mercury that high. We would typically run mercury at 100 times lower than that. Maybe 100 parts per billion typically is the highest we would run as an external standard with mercury because of residual memory factors and the stickiness factor and the plumbing of the ICP-MS. Speaking of that, I do want to explain a little bit about the sample introduction system. So I'm going to go ahead and show you that next. All right, this is the sample introduction system, and it's not actually running with live samples right now, but I do want to show you kind of how this works and give you a good idea of what all this is all about, because this is really cool. This is great stuff to understand. So I'm going to put some vials in here as placeholders, but don't think that this is real. In this case, I'll be running it later, but not with cameras on. But typically we would use this tray right here would be for external standards. So we would put our standards in here so that, and remember, the liquids are being taken out of here through this plumbing and into this sample introduction system over here, where they're turned into a plasma, a stream of plasma ions that go into the detector, the quadrupole, really, and then the detector at the end, to tell you how much heavy metal is in your liquid. So when we start over here, we're using external standards, and we have to tell the machine, what does, let's say, 10 parts per billion mercury look like? Or what does 1 part per million lead actually look like? We have a system of standards over here, and typically I'll use about 10 to 12 vials of different standards. And then we'll have the unknowns over here, like, let's say, another tray over here of things that I'm trying to test. I'll put the vials in there that have been digested. Now, this auto sampler, which, let me just kind of show you, I'll bring it up here manually. This probe right here, which goes up and down, and it goes into the liquid, pulls the liquid up, goes through this plumbing, goes through this tube, and it goes over here into the sample introduction system, which is quite fascinating. I really, let me get closer on this. I can show you a little bit. It's kind of cool. This right here is called the Niagara Plus sample introduction system, and you'll notice that the tube coming off of the auto sampler probe is right here. This goes into this bottom valve, this bottom piece right here. And this is a multi-rotor valve that actually loads up some of the sample into this loop right here. This loop is a 0.5 mil sample loop. In other words, it holds half a milliliter of sample material in here. And then the valve switches, and then it kicks it into the nebulizer, which I don't know if you can even see the nebulizer. Let me try to get a little closer over here. The nebulizer is right here. And using argon gas as a carrier to push a stream of the liquid through here, it goes into this, which is called the spray chamber, which is cooled to eliminate extra moisture in the spray chamber. It then goes through. Actually, I'm gonna open this up for you here. It goes through this transfer tube here, and it ends up over here at the. Let's see if I can give you that a little better. It ends up at the plasma torch, which is right here, and the nebulizer helps turn this into a stream of liquid, which is propelled by high pressure argon gas. It goes through the transfer tube, and I'm going to open it up just a little bit for you to show you. This is more argon gas that comes in here. It just comes on like that. This is the plasma torch, and it's really two concentric pieces of glass, one inside another, kind of glass rods, and it's very, very delicate piece of this instrument. It costs about $800 right there. And then here's an RF generator coil, which lights the plasma, and you actually get a plasma charge right here at this point that then goes into the sample cone that you really can't see here. So this system is really designed to turn well, initially solids into liquids, and then liquids into a stream of positively charged ions in a plasma gas stream. Well, gas isn't even the right word. A plasma stream that then goes into the mass analyzer. So all this jazz over here is just the plumbing, and the plumbing is, well, I'll leave that open. The plumbing is pretty intricate. This line right here is the introduction of the internal standard, and this is the injection point for the internal standard. The internal standard, we use a combination of yttrium and what else are we using? Indium, terbium, scandium, not yttrium, sorry. These have unique atomic mass numbers that make it especially suitable to use as an internal standard, so that this machine knows how to normalize fluctuations in the flow of the liquid stream into the plasma torch. So again, that's where the internal standard comes from. This is the Perry pump right here. It pulls a steady stream of liquid through these tubes, and it's not running right now, so it's not actually set up correctly. But normally this would be right here. This is the tube that pulls the sample from. Well, I should say, normally that would be the sample if I wasn't running the Niagara, but because I'm running the Niagara, this is the sample. But now this is set up to be either a rinse solution or a tuning solution to tune the detector. And then this down here is the pump for the Niagara, and this pump, when it's on, this is rotating. Actually, I can turn it on right now. Let me go over here to the control panel. I can put it into rinse mode. There it is. It's in rinse mode right now, and you can actually see that it's moving liquid through here, and this pump is rotating, and you can see the liquid coming out here. So this isn't just in a rinse mode right now, and if you look up here, this light up here is also the rinse light mode. You can change it into another mode, which is injection mode, which actually then injects the liquid stream into the nebulizer. And then this down here, in case you're curious, is really just kind of a wash solution that I use in emergencies sometimes to backwash to get clogs out of the sample uptake system. This right here is a control module that sits between the auto sampler and the Niagara system. And what this does is it coordinates of when exactly the auto sampler takes up a specific segment of liquid to be looped into the sample uptake loop here, so that the timing can be correct for introduction into the nebulizer and the plasma torch. And I bought this from Glass Expansion in Australia. They're a great company. This is an awesome product. I set it up myself. It only took really like 6 hours. It wasn't really that difficult to deal with. I'm just turning that off again. The hardware, the software, everything only took about 6 hours, so it was pretty straightforward. The system stays on 24/7, evenings and weekends included, and the vacuum pump has to run 24/7. So to try to be environmentally friendly about that, we try to put it to the best use possible, actually encouraging products that are environmentally friendly. You know, get the lead out, get the cadmium out. We use this instrument to help protect the environment and protect the food supply and empower consumers with accurate information about what they're eating. Now, you've probably seen this fume hood, this hood vent before. This is actually taking the heat out of the system, including some of the excess argon that's blown through here. The argon's under pressure. We're using about 16 liters per minute of total argon, which is a lot of argon. That costs a considerable amount of money. It's like burning $1 a minute. So every minute this is running, it's costing us $1 just in argon gas, not to mention electricity and everything else. And so that's really those are the innards of the sample introduction system. I could show you some other kind of interesting parts. I don't want to disassemble it really too much, except when I need to, but let me show you one interesting thing here, which is the nebulizer. This is the nebulizer, and it's a really amazing piece of technology. What this does is it takes a liquid input here and some argon gas here, and through a very, very microscopic series of channels, it produces an extremely high velocity stream of liquid out this end that's actually moving faster than the speed of sound. Yeah, it's over Mach 1, and this is the sea spray nebulizer, which resists clogging, which is very good because sometimes I'm digesting fruits, and I've noticed that strawberry fibers really clog these things up. So the sea spray nebulizer has been very, very good about not getting clogged when I'm running strawberry samples. Strawberries are pretty amazing. They're really good at absorbing mercury, and that's actually kind of why. So what I'm doing now is I'm reassembling the nebulizer, reattaching the argon tube, and reattaching the injection tube here from the Niagara. So we're back in business. So we're ready to go right now. That's the basics of it. We use things like this, Triton X, for cleaning. That's how it all works.